Good evening, everyone. My name is Leena Salamani, and today I will be presenting our research titled Towards Near Perfect Fish Species Classification Using Hybrid CNN Transformer Deep Learning. Fish species classification is important in fisheries, aquaculture, and marine conservation. However, identifying fish manually is time consuming, requires experts, and is difficult to scale. To address this problem, our research proposes a hybrid deep learning model that combines CNNs and transformers. Throughout this presentation, I will explain the motivation behind this study, our proposed framework, the experimental results, and the key findings. Why fish species classification matters. Accurate fish species classification has many real-world applications. It supports sustainable fisheries by helping estimate fish populations and improve fishery management. It is also useful in precision aquaculture, where fish can be monitored and sorted automatically. In addition, it plays an important role in marine biodiversity conservation and real-time underwater monitoring. For this research, we used two datasets. The first contains 9,000 images of 9 fish species, while the second contains 27,370 images of 23 species, making it a more challenging dataset. Overall, the goal is to reduce manual identification while creating a faster and more accurate recognition system. As per the research gap, previous studies mainly used either CNNs or transformers. CNNs are very good at learning local features such as scales, fins, textures, and body shape. However, they have difficulty capturing the overall relationship within an image. Transformers, on the other hand, are excellent at understanding global context through self-attention. However, they require larger datasets and may lose fine local details. Since both models have complementary strengths, our research combines them into a hybrid architecture that learns both local details and global context. This slide illustrates our proposed hybrid framework. The fish image is first processed by ResNet50, which extracts local features such as scales, texture, and body shape. At the same time, the image is processed by Swin Transformer, which captures global relationships across the entire image. The features from both models are then combined using feature-level fusion before being passed to the final classifier. As a result, the model learns both detailed morphology and overall image context, making it more effective at distinguishing visually similar fish species. To evaluate our approach, we compared three models: the ResNet50 CNN, the Swin Transformer, and our proposed hybrid model. The data sets were divided into 50% for training, 30% for validation, and the rest 20% for testing. Training was performed using the Adam optimizer and cross-entropy loss, while Optuna was used for Bayesian hyperparameter optimization. Finally, the models were evaluated using accuracy, precision, recall, and F1 score. Now let's look at the results. For the primary data set, both the CNN and the hybrid model achieved 100% accuracy, while the transformer achieved 86.33%. For the more challenging secondary dataset, the hybrid model achieved the highest accuracy of 99.51% compared to 99.43% for CNN and 93.15% for the transformer. Although the improvement over CNN is small, it shows that combining local and global feature helps the model perform more consistently when classifying a larger number of similar fish species. So what the results mean? These results show that the hybrid model performs especially well as the classification task becomes more complex. For simpler datasets, CNNs already perform very well because local features are enough. However, for datasets with more species and greater visual similarity, combining local morphology and with global context improves the model's ability to distinguish between similar fish. This makes the hybrid model more suitable for real-world applications in fisheries, aquaculture, and biodiversity monitoring. In conclusion, this research shows that combining CNNs and transformers produces a more robust and accurate fish classification model. The proposed hybrid model achieved 99.51% accuracy on the challenging 23 species dataset while maintaining excellent performance on the smaller dataset. In future work, the model can be tested on more diverse underwater datasets, optimized for real-time deployment and enhanced using explainable AI. Thank you for your attention. I would be happy to answer any questions.